Hello, everyone. Thank you for listening to my talk. My name is Dylan Paré, and I am a graduate student at the University of Iowa, working with Dr. Cornelia Lang. And today I'll be talking about an aspect of my PhD thesis work, which is on the Galactic Center radio arc. This is a radio image of the Galactic Center taken using Meerkat at a frequency of about 1 gigahertz. The Meerkat is an interesting region to study because it is by far the closest galactic nuclear region to the Earth at about only 8.0 kiloparsecs away. And because of its proximity to the Earth, we can study it in far more detail than we can any other galactic nuclear region. And in that region, we see elevated temperatures, densities, and magnetic field strengths compared to what's observed in other regions of the Milky Way, like the galactic disk. There's also the central black hole of the galaxy within the GC. It's within this Sagittarius A region, which I've marked here. And then there's also a number of thread-like structures seen throughout the GC that are known as the non-thermal filaments, or NTFs, because of their non-thermal synchrotron emission. And one such NTF system, known as the radio arc, which is quite close to Sagittarius A star, is the focus of my talk today. So before going into the details of my work on the radio arc, I just want to briefly summarize some of the key properties that have been observed in the NTF population as a whole. So the NTFs are far longer than they are wide, leading to their thread-like appearance. They're highly polarized, with percentage polarizations generally greater than 50%. And while they have continuous total intensity distributions, their polarized intensity tends to be patchy or discontinuous. Because of their non-thermal emission, you can determine rotation measure values towards these structures, allowing you to correct for Faraday effects along the line of sight. And then having corrected for Faraday effects, you can determine the intrinsic magnetic field distributions local to the NTFs. And so looking at the rotation measure values first for the NTFs, they're generally found to have large rotation measure magnitudes of a few hundred to a few thousand radians per meters squared. And these are quite large rotation measure value or rotation measure magnitudes compared to what's seen in the galactic disk or in extragalactic sources. And then using these rotation measures and correcting for the intrinsic magnetic fields, they're generally seen to be parallel. The magnetic fields are generally seen parallel to the total intensity of the NTFs. So turning now to my work on the radio arc, for my master's work in 2019, we used a VLA data set to determine the intrinsic magnetic field of the radio arc. And so on the left here, I'm showing an image of the radio arc at 2 gigahertz from our VLA data, just showing the details of the radio arc system. It's made up of multiple individual filaments closely packed together. There's also local to the radio arc a few H2 regions, as well as some larger structures possibly enveloping the radio arc. And then at higher frequencies, at 10 gigahertz, I'm showing our resulting intrinsic magnetic field after we correct for Faraday effects using rotation measure. And rather than the radio arc having a uniformly parallel magnetic field as seen for other NTFs in the GC, we found in this work an alternating magnetic field pattern where we had regions of parallel magnetic field as we expected, which are marked with these rectangular zones, but they were interspersed with regions of rotated magnetic field that are marked with these elliptical regions. And in this study, it was unclear what was causing these regions of rotated magnetic field. So to follow up on this VLA work, for the first part of my PhD thesis, I conducted observations of the radio arc using the Australia Telescope Compact Array ATCA telescope in order to get a better sense of some of the Faraday effects towards the radio arc. So this is a total intensity image obtained using our follow-up ATCA data. And you can see that we obtain the same basic features, or basically resolve the same features we saw in our VLA data. We pick out the same filaments observed in the VLA and also the same H2 regions. And this yellow box here marks the region of polarized intensity for the radio arc. And one of the key advantages of this ATCA data set is that it covered a large frequency range from 4 to 11 gigahertz, and it did so contiguously with a 2 megahertz frequency resolution. And so this large frequency range and high spectral resolution allows us to do more sophisticated modeling of the Faraday effects observed along the line of sight. And this figure I'm showing here just shows a sample spectra for a sample line of sight within our data set covering our full 4 to 11 gigahertz frequency range. And these are two snapshot 2D images of our polarized intensity at 5,000 and 8,500 megahertz for the radio arc. So to do our modeling of the Faraday effects, we focused on 8 target pixels, and we chose these target pixels to cover the full area of polarization obtained for the radio arc. They were also generally in regions of peak polarized intensity, as shown in this grayscale image here. And they were also chosen to cover regions of both parallel and rotated magnetic field orientation. So if you look at this figure, we've overlaid the same pixel locations onto our 2019 magnetic field distribution obtained from the VLA. And pixels 1 through 4 are located in regions of parallel magnetic field, whereas pixels 5 through 8 are located in regions of rotated magnetic field. And the method we used to model the Faraday effects for these 8 pixels was to fit depolarization and Faraday mechanisms simultaneously to the Stokes Q and U linear polarization products. And doing this method allows us to model for multiple different effects along each line of sight, which we would expect to be the case towards the radio arc since it's within the galactic center and we're observing it through both portions of the galactic center as well as multiple spiral arms. So doing this kind of modeling grants us improved understanding of some of the physics that are causing the polarization and properties that we're observing for the radio arc. So we modeled for mechanisms that give us information on both external and internal Faraday effects. And this figure I'm showing here is just showing an example of this kind of modeling that was done on some external or extragalactic sources. So the modeling, to go into that in full detail would take a while and would take longer than I'm able to do in this talk. So just to briefly touch on the results of this modeling, we ended up determining that external Faraday effects were the most likely mechanism causing the rotation observed towards the radio arc. And this was found to be the most likely for all 8 pixels. So this was true regardless of whether the pixel was in a parallel or rotated magnetic field region. However, we did see a systematic difference if we looked at the IFD model, where the parallel magnetic field regions systematically evaluated the IFD models as more likely than in the rotated magnetic field regions. And so this trend in the IFD model could indicate a systematic difference between parallel and rotated magnetic fields, possibly indicating different Faraday mechanisms or different media being encountered along those different lines of sight. And in order to follow up on this work and more conclusively understand what could be going on here, we would want to model these regions incorporating additional media into our models. And so in conclusion, We found slight evidence that there are different Faraday effects being encountered along the different lines of sight. And to kind of follow up on this work would require more comprehensive modeling of multiple media along the line of sight, which is a future work we have planned to continue to build on this analysis. Thank you very much.